Hey guys, welcome to Pre-Calc, lesson 8A.4, compound interest and half-life. All right, first example here. Let Y represent the mass of a quantity of a radioactive element whose half-life is 25 years. After T years, the mass in grams is given by Y equals 10 times 1/2 to the T over 25. What is the initial mass? Well, the initial value is always the A value in front right there, so that's pretty straightforward, 10 grams. How much to the nearest hundredth of a gram of the initial mass is present after 80 years? So 80 years, we would say T equals 80, and we just plug that right into the calculator. That would give us Y equals 10 times 1/2 to the 80 over 25. All right, nearest hundredth of a gram, I got 1.09 grams. Find the percent change. So this is actually where it gets a little bit more challenging. Percent change. So what needs to happen, if we take a look at the original function, I need this t to be by itself, which means I need to get this 1 over 25 exponent and bring it inside. Okay, so in doing that, I would get something that looks like this. Y equals 10 times, I'll use 0.5 instead of 1/2, to the 1 over 25 power, and then I still have this t on the outside. That's going to be 10 times 0.97265 to the t. So your percent change, remember, is how far this growth factor is from 1. So usually when it's less than 1, it's a little bit more challenging. What I would do here is take 1 minus 0.97265. That gives me 0.02735. To the nearest tenth of a percent. So first, I would have to get the percent. That would be 2.7345, and then round this, so that stays 2.7. So this is going to be 2.7% decrease. Why is it a decrease? Because this B value here is less than 1. Okay. So next what we're going to do is, if you had time, we would do this in class. Unfortunately, we don't. But if you want to try this at home, put this into Y1 in your calculator. Go to your table and set the independent variable on ask and throw in 10, 100, 10,000, 100,000, a million. And what you're going to see is this pattern. At 10, it's going to be 2.5937. At 100, it's going to be 2.7048. At 10,000, it'll be 2.7181. At a million, it'll be 2.7183. And if you notice, these numbers are getting closer and closer and closer to a specific value. That value happens to be what we call E. And E is a limit. E equals this algebraic expression as x approaches infinity. So as x approaches infinity there and infinity there. That value to a few decimal places is 2.7182818, so on and so forth. Now it's irrational, so like pi, it'll never repeat and it'll never terminate. E shows up quite often in exponential functions, especially continuous models, continuous growth. So here's an application that uses E. It says a colony of fruit flies grows at a rate that is modeled by the function f of x equals 15 times e to the 0.728 t, where t is the number of days. All right, so our unit of time in this case is days. Find the number in the colony at the start of the observation. That is simply our initial value. That is 15. Pretty easy to get by now. The number of fruit flies after 6 days. So f of 6 will be 15 times e to the 0.728 times 6. Since we are talking about fruit flies, a biological entity, we can only deal with whole numbers. So what you want to do here, usually it'll say round it to the nearest fruit fly. If it doesn't, technically you should probably truncate the decimal instead of rounding up. So this would get Us 1183, 1183. Number of fruit flies after 12 days. Okay, it's just another calculator exercise. Throw in a 12.728 times 12. And in your calculator there, it would give you 93,344. So this is actually a good example of exponential growth, not linear growth. You look at this and say, oh, 6 days. Well, there's twice as many days, so maybe it's double this. It's not. That's linear. This is exponential. Double the amount of time, but many, many, many more times that in terms of the population. Exponential. Think of that graph. It goes like this, zooms upward. Okay, the percent increase per day. Here's where it gets a little bit challenging. What we need to do is we need to take this original function here, and we need to figure out what the b term is. The b term would be e to this exponent. You basically want the t all by itself. Okay, so to do that, I would have something that looks like this. F of t equals 15, and then I'd calculate e to the 0.728 to the t. So that's 15 times, I got 2.07093 to the t. So this is our AB to the x, or AB to the t. So now if you want the percent increase per day, we have to take this and subtract 1. Notice this is more than 1, so obviously it's increasing. So I would do well, I'm actually not going to do that. It's pretty easy to do. Subtract 1 from that, and you get 1.07093. And it just says percent increase. I'll go to the nearest, I don't know, tenth. So if you notice, you move your decimal over 2 places here. This would round up to 1, so it's 107.1% increase. So it's more than doubling every day. All right, next example, half-life. The half-life of a certain radioactive substance is 840 years. The amount present after t years is modeled by this function. So this is our standard half-life formula. Here's our initial amount, A. Since it's half-life, this is always 1/2. And it's t, the amount of years, over, that is the half-life of the substance. So if the half-life is 240 years of the substance, it goes there. If the half-life is 1 million years, then that's 1 million. So they already give you this. Find the amount after 50 years. Okay, so we're going to plug in 50. That'll be 80 times 0.5 times 50 over 840. And it doesn't say what to round to. I'll just go nearest thousandth. That I got 76.766. Now, does this make sense? Let's think about it. The half-life is 840 years. That means in 840 years, half of this would remain. So that's 40. Well, 50 is a lot smaller than 840. So it shouldn't even be close to half of the substance. And it's not. This is a lot closer to 80 than it is 40, which makes sense because this time period is much smaller than the half-life of the substance. Now you can predict this after 1,000 years. Well, 1,000 is more than 840. So I'm expecting this answer here to be less than 40. So maybe like 36 or 38 or 34. I don't know, but it's going to be less than 40. You know that already. So let's plug that in. A of 1,000. 80 times 0.5 times 1,000 over 840. Throw that into the calculator. What do we get? 35.0527 out of a few places. Again, which makes total sense. I know it's going to be a little bit less than 40. Now, what is the percent decrease per year to the nearest hundredth of a percent? So what we need to do for percent decrease, remember, is I need to take this 1 over 840 exponent and move it inside. The t has to be all by itself. So that will look like this. A of t equals 80 times 0.5 to the 1 over 840th to the t. Okay, so that's 80 times 0.999175 to the t. So now your percent decrease, I know it's a decrease, that's less than 1. Percent decrease will be 1 minus 0.999175. That is 0.000825. To convert that to a percent, we move this 2 places. So my decimal would go right here. Nearest hundredth of a percent. So there's my decimal. There's the hundredth. That's a 2. So that will stay 8. 0.08. 0.08% decrease. Which hopefully makes sense. What is the percent decrease per year? It shouldn't be that much because the half-life is 840 years. So in 840 years, I'll have half of this. It'll decrease 50%. So that kind of makes sense. It's not decaying really that much per year. All right, 2 formulas you're going to become very familiar with. Compound interest. We have compounded n times a year. So n could be 365 if it's daily, 12 if it's monthly, so on and so forth. 4 if it's quarterly. This is our initial amount. R is our interest rate as a decimal. N is the number of times it's compounded, and T is time. Now, if it's compounded continuously, we use this formula, which is kind of known as PERT, P-E to the R-T. That is continuous compounding. So I'm going to do an exercise here, this chart. We are going to invest $2,000 at 8%. And we are going to find the different end amounts when we compound annually, quarterly, monthly, or continuously. Okay, so try to keep up. Annually, n equals 1. So after 1 year, A equals 2,000 times 1 plus 0.08 to the first, or A equals $2,160.00. So after 2 years of this, A equals 2,000 times 1.1 plus 0.08 squared. So here I got 2,332.80. 10 years, A equals 2,000 times 1 plus 0.08 to the 10th. So that was $4,317.85. Compounded quarterly, n equals 4. Okay, so that's going to be A equals 2,000 times 1 plus 0.08 over 4 times 4 times 1, or 2 to the 4 times 1. And I got $2,164.86. Here, 2 years, A equals 2,000 times 1 plus 0.08 divided by 4 to the 4 times 2. So that is $2,343.32. And here, A equals 2,000 times 1 plus 0.08 over 4 to the 4 times 10. So that will be $4,416.08. Monthly, n equals 12. So A equals 2,000 times 1 plus 0.08 divided by 12 to the 12 times 1. So that was $2,166.00. Here, A equals 2,000 times 1 plus 0.08 divided by 12 to the 12 times 2. So that was $2,345.78. The last one here, A equals 2,000 times 1 plus 0.08 divided by 12 to the 12 times 10. So that is $4,439.28. And lastly, continuously, which means we're using this formula. All right, so A equals our principal 2,000 times E to the 0.08 times 1. So that was $2,166.57. Here, A equals 2,000 times E to the 0.08 times 2. So for this one, we got $2,347.02. And lastly, A equals 2,000 times E to the 0.08 times 10. So here I got $4,451.08. You don't actually have to write down all these values, but what I want you to notice, all right, when it comes to compounding once, 2160. Compounding continuously, 2166. So a $6 or $7 difference. When you get to the end here, 4317, 4451. So a little bit more than $100 over 10 years. Yes, you get more money the more times you compound, but it's not a drastic difference. What will increase your money more is time and interest rate. The interest rate has much more of an impact on your growth than compounding does. Okay, so let's try another example. Calculate the following investments. $6,000 at 4% compounded quarterly for 1 year. So obviously you need to be able to do this. So compounded quarterly for 1 year. N equals 4. Initial amount is $6,000. 6,000 times 1 plus our interest rate 4% is 0.04 divided by the number of times it's compounded. So that's 4 to the 4 times how many years? And then we're just going to throw that right into the calculator. $6,243.62. Okay, how about $15,000 at 12% compounded continuously for 3 years? So this is a different formula. This is our Pert formula. All right, it'll look like this. A equals 15,000 times E to the R, so that's 0.12, times the number of years, 3. We'll throw that into the calculator, and that gives us $21,499.94. Again, another one, calculator exercise, 10,000 at 15% compounded monthly. So N equals 12. This will be A equals 10,000 times 1 plus my interest rate, 0.15, divided by 12 to the 12 times the number of years. So notice in this compound interest formula, these two numbers are always the same. And it hopefully kind of makes sense to you, because what we're doing is we're taking our annual interest rate, dividing it by the number of times we compound it. So this ends up being smaller than what it would be for a whole year. So to make up for that, you take that number of times you compound it and multiply by the number of years, because you're just calculating interest more times. Okay, so that value gives me $21,071.81. All right, and lastly here, good question. It says, what is the maximum interest that can be earned on $100,000 when invested at 8% for 2 years? So it doesn't tell you how many times it compounded. But you need to understand that maximum interest occurs when you compound it the most amount of times. So this, whenever you see maximum, is compounded continuously. So minimum then would be compounded once. So I'm going to use my Pert formula. A equals 100,000 times E to the R, what's that, 8%, 0.08 times the amount of time, 2 years, and that would give me $117,351.09. So that's the most interest you're going to get on 8% over 2 years when you compound it continuously. All right, our last example, annual rate of return. This is something that's pretty important, and it's kind of interesting here, especially those that go on into the financial world. It's the percent increase or decrease of your investment, including all compounding and or dividends. So we don't talk about dividends in this course, but we will talk about compounding. It's not always the same as the interest rate. So the interest rate is the annual rate of return when you compound it once a year. So if your interest rate is 7% and you compound it once a year, you get 7% back. But if you compound it more than once a year, it's going to be more than 7%. Not a lot more, but it will be more. So in this example, we're going to calculate the annual rate of return on 3 different investments. All right, and it says here to the nearest thousandth of a percent. Okay, so $9,500 at 7.5% compounded annually. Oh, well, if you want compounded annually, we just said the annual rate of return equals your interest rate. So that's simply going to be 7.5%. It says since it says 1,000, okay, I'll go out that many places. Okay, so 9,500 at 7.5% compounded monthly. So this formula would look like 9,500 times 1 plus 0.075 divided by 12, all right, to the 12t. Well, remember, what we are going to do is get this number inside. So I just want the t by itself. I don't really need to bring this 9,500 along, so I'm just talking about the interest rate. But so this will be 1 plus 0.075 over 12, that whole group to the 12th to the t. Okay, now if I calculate that, let's see what I get. I got 1.077632 to the t. So what I need to do now is take this value and subtract 1 from it. All right, so if I do that, that gives me 0.077632. Then I have to calculate to the nearest thousandth of a percent. So I move this over 2 places. So my decimal point goes here. 1, 2, 3. That's a 2, so that stays a 3. So I'm going to get 7.763. That will be my percent increase. Now notice, this said 7.5%, but since you compound it monthly, you end up getting 7.763% increase for the whole year. And that's kind of the cool aspect of compound interest. This last one here, 9,500 at 7.5% compounded continuously. So this is what the formula would look like, times e to the 0.075 t. So what I need to do now is I need to calculate this. Okay, so that's 9,500. E to the 0.075 is 1.077884 to the t. So again, what I need to do is take this value, subtract 1. Okay, so that is 0.077884. Move that decimal 2 places, round to nearest thousandth. So I'd get 7.788, right? That's a 4, so the 8 would stay. 7.788% increase. So again, if you notice here, 7.5% becomes this when I compound it continuously. So you might see a question that says, what is the maximum annual rate of return on a 7.5% investment for the year? That would be 7.788. That's the maximum. What is the minimum? Well, the minimum is 7.5. If you just compound it one time, it's 7.5. Continuously, it can get as high as that. Okay, so that concludes day 4. Thanks for watching, guys. As usual, reach out if you have any questions, and hope to see you in class soon.